Without a doubt, modelling is a very strange activity, and indeed philosophers of science have reflected upon the kind of knowledge that models produce. And that's because the reason we use models is to deal with situations where our observations are either impossible to make, or difficult to make, or dangerous to make. They might relate to the future, for instance, so you can't observe the future. And so models then are clearly something that sits a little bit differently with conventional scientific method. And more interestingly, raises the question, how is it you distinguish a mathematical model of the future from a crystal ball? What makes your crystal ball a mathematical model? What are the things that we do as modelers to do that? And of course, when you look in the literature, there is a huge sort of spectrum of things that the modelers will do, that I do routinely, to help me convince myself that I'm not simply making crystal balls, I'm making models. I think the classic thing that we do is we run the models on historical data. So we try and predict the past because we know what the past is. We think we know what the past is. And in doing that, we can then say, does our model reproduce the past? And if it doesn't reproduce the past, we can ask ourselves why. And if need be, we can start to change the model. Things become a little bit more complicated, unfortunately, because all of our models strip the world down to what we assume is very important. That's why we have to model. We have to validate the models. We have to test them on the past. But in doing that, we introduce a whole series of falsifications, approximations, shortcuts to help make our model work, that we have to do because we don't have the data, we don't have the understanding, we can't solve our models numerically with the right space and time resolution, so we have to make them coarser, poorer resolution. And that introduces things into our model that we can simply call parameters. And those parameters often have a very influential effect on what your model predictions are. So your model has to be made to work. You've got to change your parameters. You've got to tune your parameters. And when I explain it to students, I often say, well, I know what the answer is. I've got to make my model produce that answer. I've got, if you like, to cheat. Now, there's a very nice philosopher of science called Naomi Oreskes, and she talks about forcing empirical adequacy, which is what modelling is all about. You have a model, you've simplified it, you stripped it down, you can't make it any more complicated, then you've got to make it work. And you do that through this parameterization process. But you also have to do that on historical data. So you then end up with all sorts of difficult strategies that you have to think about. I've got my model to work on my historical data. Can I now use my historical data to say that my model works? Well, no, so you have to do a split test where you split your data in time, or you model one place and then you parameterize it and then you try and apply the model and test it in another place. There's a series of things that we have to do. But all of this cannot escape the fact that with no past, there is no model of the future. So the past becomes encoded through what we do in the present to model the future.